everybody, and welcome back for our Unit 5 Lesson 7 video, which is all about something called curve sketching. So we have one learning target for today. I can identify key features, which would be critical points, increasing, decreasing, concave up, concave down, points of inflection, maxima and minima, all the stuff that we've been talking about, using first and second derivatives of a function, and use these key features to sketch the graph of a function. So after we identify the key features, the locations where a graph is increasing, decreasing, etc., we then want to be able to sketch a picture of the graph of a function. So since we are often asked to sketch a graph of a function using the information about the function and our knowledge of derivatives, what I want to do is kind of summarize what we know so far based on the first and the second derivative. So you'll notice here it says f prime of x is greater than 0. That means uphill because the first derivative is positive. And you'll notice here it says f prime of x is less than 0. That means the graph must be going downhill because the first derivative is negative. Here it says the second derivative is positive, which means we would have a function that is concave up. And here it says that the second derivative is negative, which means we have a function that's concave down. Now, the reason I'm going over this again is because when we have a graph that is concave up, for example, part of this graph is going downhill. If you look at the left side of the curve, part of the graph is going uphill if you look at the right side. Same thing with a function that's concave down. You could also have a function that's going uphill but curved kind of in a concave down way, or uphill and curved in a concave up way. So one of the things we're going to be doing is combining the information that we know about the first derivative with the information that we know about the second derivative to get a very good idea of the overall picture of a graph. For example, if we know that the first derivative is positive, therefore the graph is going uphill, and the second derivative is also positive, therefore the graph is concave up, then the graph must look like the right side of this curve, uphill and concave up. So that's going to tell us that on our graph, that portion of the graph looks like this. If we have a graph that is going uphill, the first derivative is positive, but is concave down, that's going to tell us that that portion of the graph must look like this. If we have a graph that is downhill but concave up, it's going to tell us that that portion of the graph looks like this. And if we have a graph that's downhill but concave down, it's going to tell us that that portion of the graph looks like this. So you can see that instead of drawing full curves that look like smiles and frowns, we're going to be drawing pieces of that depending on whether that portion of the graph would be going uphill or downhill, in addition to whether it should be concave up or concave down. Now, here is a very typical style of question that we're going to be given and the types of questions we will be asked. It says, use the table to answer questions about f of x. Then sketch the graph of a function on the axes provided. Now, in this table, we're given a lot of information. So before we try to answer any questions, I just want to make sure you know what information is here. The first row of the table is telling us x values. So when x is 0, x is 1, 2, 3. And then if you look here, it says 0 is less than x is less than 1. So in other words, x is between the point where x is 0 and the point where x is 1. What this is doing is telling us what's happening specifically at certain points on the graph, as well as over intervals of the graph. So in the section between 0 and 1, here's some information about what's happening. The second row is telling us the y values, or the function values of the graph. So these are the output values of the function. For example, when you plug in the number 0, you get -1. Now, in between 0 and 1, all of the y values are negative. Then when you plug in the number 1, you get 0. And then in between 1 and 2, all of the y values are positive. And then when you plug in 2, you get 2, etc. The third row here is telling us information about the first derivative. So I should probably write some of this on here. I am so sorry for being a little bit negligent here. So this is telling us the y values of the function. The second row is telling us the first derivative. So this is telling us whether the function is increasing, which means going uphill, or decreasing, which means going downhill. So, for example, it's telling us that when x is 0, the first derivative is 4, which is a positive number, so the graph is going uphill. Now, between 0 and 1, the first derivative is always positive. Since the first derivative is always positive, we know that this portion of the graph is going uphill. Then at 1, the first derivative is 0. Since the first derivative is 0, that's going to be a critical point of the function, because critical points are places where the first derivative is equal to 0 or is undefined. If the first derivative stays positive, that means it continues to go uphill, the graph that we're drawing. And then when the first derivative does not exist, that's going to be another critical point of the function. When the first derivative is negative, the graph that we're drawing is going to go downhill, and then it stays negative. It's still a negative number, it's -3, and then it stays negative again for the next part of the graph. Now, what I just did by drawing in these little arrows and labeling the critical points is part of the strategy that we're going to use to get this problem accomplished, to kind of do what we need to do here. So you need, when you first see a chart like this, to go through and draw little mini pictures and label things in the chart. It's going to make your life easier at the end because you did that. All right, last but not least, we're going to talk about the second derivative. Now, the second derivative is going to tell us whether our graph is concave up or concave down, and it's also going to help us figure out the points of inflection, which I'm going to abbreviate POI. So the first thing to notice is that at 0, the second derivative is negative, and in between 0 and 1, it stays negative. So my function is concave down, like a frown. Then my second derivative is 0. Now, I'm not going to label that as a point of inflection because just being equal to 0 does not make this a point of inflection. We have to see if the concavity actually changes. So what I'm going to do is look after that and see, oh, now the second derivative is positive, so concave up. Since the concavity changed here, this is going to be a point of inflection. Then the second derivative does not exist, and then the second derivative is negative, which is concave down. Once again, the second derivative changed signs, and therefore this is another point of inflection on the graph. And then the second derivative is 0, and then the second derivative is positive. So once again, the second derivative changed signs. So this is another point of inflection on the graph. Okay, once you've kind of got your table labeled and you have little pictures drawn to help you remember and kind of keep this organized in your mind, it's a little bit easier to answer some of these questions. So let's talk about critical points. Well, we labeled the critical points in the table. We said the critical points were when x was, if I look here, 1, x was, if I look here, 2, and then that was it. I don't think there were any other critical points. We can also figure out points of inflection. So points of inflection were where x was 1, when x is 2, and again when x is 3. Now for increasing, we're going to look at the row that tells us about the first derivative, and we're going to try to figure out where it's positive. So in this case, it's positive between 0 and 1, and this endpoint is 4 and this endpoint is 0. So I'm going to use closed brackets, which means between 0 and 1, my function is increasing. Now it continues to stay positive, but you'll notice that here it says that the first derivative is undefined. This is the only time, besides arrows or infinities, where we would use an open bracket, because you can't include a point as being increasing if the derivative is undefined there. So you would also say that the interval from 1 to 2 is increasing, but I'm going to use a parentheses there because I'm not including the number 2 since that's a place where the derivative is undefined. Let me make a note of that. I'm using this because it's DNE here at the endpoint. Decreasing would be between 2 and 3, and once again I'm going to use an open circle at the 2 because the derivative is undefined. And then also from 3 to 4, it looks like it is decreasing. Now, as far as concavity goes, we're going to look at the second row of the table. So concave up is going to be this section right here, which is between 1 and 2. And for concavity, we're always going to use parentheses. We're always going to keep them open. So I don't think we need to really go through that again. For the next interval that's positive, it would be between 3 and 4. And for concave down, I would be looking at this first interval here between 0 and 1. And again at this interval here between 2 and 3. Now, once we've identified all of those values, we can actually make our graph. We're going to use the information from the table to make the graph, and we're going to start with the y values. Now, you'll notice we haven't talked very much about the y values yet. This is the first time that those y values really become important, is when we're sketching the graph. So we know that when x is 0, y is -1, so I would put a point there. When x is 1, y is 0, I would put a point there. 2, 2, put a point there. 3, 0, put a point there. Now I'm going to connect the dots, but I'm going to connect the dots in a strategic way. If I have a graph, for example, between 0 and 1 that is going uphill but concave down, it must look like this first half right here. It must be this part. So when I connect these dots, I'm going to draw it very obviously concave down and uphill. The second part of the section of the graph is going to go uphill but be concave up. So it must look like this part of the graph right here. So I would, again, very clearly make that concave up and connect those dots. Then it's going to be downhill and concave down. So I'm going to be looking at this kind of half of that curve. So it's going to go like this. And lastly, it's going to be downhill but concave up. So it's going to look like this. And it's going to go downhill but be concave up and stop at 4 because that's where this graph stops. Now you'll notice we don't have a specific y value for 4, so it doesn't really matter where you stop as long as you stop at 4 here. You could go like down a little bit further if you wanted to, it doesn't really matter. One of the other things that you should always stop and check at the end is that this all makes sense as a big picture. So we should know that the y values are negative between 0 and 1, which means below the x-axis, which is true based on our graph. Positive, which means above, positive, which means above, negative, which means below. Then we should go, okay, are we going uphill, uphill, downhill, downhill? And then are we concave down, concave up, concave down, concave up? And just kind of go through at the end and make sure that you confirm that your results make sense overall as you connect them to the table. All right, next, how are we going to do this if we don't have a table of values? Well, the answer is you're going to make your own table of values. So if you're given this function and you're asked to sketch a picture of the graph, then you're going to need to kind of make your own big mega table like we did in the previous problem that has rows for the first and the second derivative. So let's go through this process so you can kind of see what it looks like from start to finish. Step number 1 is going to be to find the first derivative. So my first derivative here would be 3x squared minus 3 equals 0. We're setting that equal to 0 so that we can find the critical points. Now, if I factor out the number 3, I get x squared minus 1, and I can continue to factor here. So I would have x plus 1 and x minus 1, which means I'm going to get two values, x equals -1 and +1. Now, right away, I know that those are the critical points. Because all that it takes to be a critical point is to have a derivative that's equal to 0 or undefined, does not exist. Okay, so now we've kind of done the first derivative stuff, at least as much of that as we're going to do for right now. Let me see if I can get this to focus a little bit. There we go. All right, the next thing we're going to do is look at the second derivative. So for the second derivative, I'm going to actually find the second derivative, which is f double prime of x is equal to, it would be 6x, and I'm going to set that equal to 0, and I'm going to solve. Now, there's nothing to really factor here. We would just get x equals 0. And that is a potential point of inflection, but we can't be sure that it's a point of inflection because we don't know if the concavity actually changes signs there. So I'm going to write point of inflection, but I'm going to put a question mark because we still don't know for sure if this is a point of inflection or not. Now, next, we're going to make a table. And here's how we're going to make our table. We're going to take the values that we found from the critical points and the points of inflection and put them into one mega table. So here's how this is going to work. Negative infinity will be the beginning. And then we're going to put these points in order. So -1 was one of the critical points. 0 would come next. That was the potential point of inflection. Then +1, and then infinity would be at the end. Now, this table is going to have 2 rows, 1 row for the first derivative and 1 row for the second derivative. So I'm going to make it a little extra tall here, just so that I have space for 2 rows. You'll notice that this table looks like a hybrid of the 2 types of tables, the sign charts that we've made before. We just do the first derivative or we just do the second derivative. Now we're just including both in one big chart. The first row here will be for the first derivative, and the second row here will be for the second derivative. Now we're going to pick a number from each section and test them in our derivatives. So in the first row here, the first number that I'm going to test is maybe -10. If I plug in -10, I get a positive times a negative times another negative. And a positive and a negative make a positive, which means the original graph was going uphill during this section of the graph. Now, in between -1 and 0, I would pick a number like -1/2. And if I plug that in, I get a positive, positive, negative. A positive times another positive times a negative makes a negative, which means the original graph was going downhill here. Then if I pick a number between 0 and 1, like +1/2, I get positive, positive, negative again, which means the function continues to go downhill here because that makes a negative. And then if I pick a number bigger than 1, like 10, and I plug that in, I get positive, positive, positive. And if everybody's positive, the final answer is positive, which means the original graph was going uphill here. Next, I'm going to do the second row of the table. So I'm going to go ahead and take those same numbers and just plug them into my second derivative equation. Now, this is just 6x. So if I plug in -10, I get a negative, which means this graph is concave down at the beginning. Then if I plug in -1/2, I get another negative, which means it stays concave down. Then if I plug in +1/2, I get a positive, which means it becomes concave up. And then I get another positive when I plug in 10, which means it stays concave up. Now, right away, one of the things I'm thinking about is we can confirm that this really is a point of inflection because this really does change concavity here from negative to positive. So yay, we've confirmed this really is a point of inflection. We weren't sure, but now we know. Now, how are we going to find the critical points, increasing, decreasing, points of inflection, concave up, concave down? Well, we're going to do this the same way we did it in the other problem, only now we just had to make the table ourselves. The critical points would occur at x equals -1 and +1. And I know that because those are the places where the derivative was equal to 0 when I solved. And the point of inflection is going to occur at x equals 0. And I confirmed that by making my table and seeing if it actually changed concavity there. For increasing, I'm going to look for where this row of the table at the top row is positive. So that would be from -infinity to -1, and also from +1 to infinity. And for decreasing, I'm going to look for the first row of the table is negative, which would be from -1 to 1. Now for concave up and concave down, I'm going to look at the second row of the table. So I'm going to be concave up between 0 and infinity because I'm concave up this whole time. And lastly, I'm going to be concave down between -infinity and 0 because, again, I'm concave down this whole time. Okay, now we're going to sketch a graph. The one thing that's missing here that we had in the other problem but we don't have here is the actual y values of the function. So what I'm going to do now is I'm going to go back up here and I'm going to actually calculate the y values for the important x's. Now the important x's here would be the -1, the 1, and the 0. The points of inflection and what we now know is the critical points and what we now know is a point of inflection. And I can find those function values by substituting into the original equation up here. So again, I want to find the y values. So I'm going to use the original. So f of -1 would be -1 cubed minus 3 times negative 1 minus 2. Now that gives me negative 1 plus 3 minus 2, which is 0. Next, I'm going to plug in 0. So f of 0 would just be 0 cubed minus 3 times 0 minus 2, which is just negative 2. And then I'm going to find f of 1, which is going to be 1 cubed minus 3 times 1 minus 2, which is going to be 1 minus 3 minus 2, which is negative 4. I'm going to start by graphing those points. So negative 1, 0, 0, negative 2, and 1, negative 4. Then I'm going to connect the dots, but using the features that I've identified in my table. So on the left side of the negative 1, so basically like over here, we are supposed to be going uphill but concave down. So that's going to be this half of that curve. So uphill but concave down looks like this. In between the negative 1 and the 0, we're supposed to be going downhill but concave down. So it's going to be this half of the curve, like this. Then I'm going to go downhill but be concave up, so like this. And last but not least, I'm going to go uphill but be concave up. So that means I'm going to go like this. And that would be your sketch of your curve. Okay, that is it for today. Thank you guys so much for watching, and I will see you soon for some practice.